Interested in the wonders of physics? Then this video is for you. I have prepared for you 10 scientific facts about physics that will shock you. Are you ready? Here we go. The ground isn't solid. While it feels firm under our feet, the ground, and everything else for that matter, is mostly empty space. Atoms themselves are mostly empty space with tiny, dense nuclei at their center. The idea that seemingly solid objects are mostly empty space is a counterintuitive fact that physicists have known for over a century. Let's take a deeper dive into how this works. First of all, imagine a giant stadium. In the center, there's a tiny marble. That's the nucleus of an atom, incredibly dense and containing most of the atom's mass. The vast majority of the stadium, representing the space between the nucleus and the outskirts of the atom, is completely empty. This empty region is where electrons whiz around, but they're so small compared to the nucleus that they contribute almost nothing to the overall mass of the atom. Even though atoms are mostly empty space, there are forces at play that prevent them from collapsing in on themselves and everything else around us. These forces are electromagnetic force. Electrons have a negative charge, and protons in the nucleus have a positive charge. Opposite charges attract, so electrons are held in their orbitals by the attraction to the positively charged nucleus. Strong nuclear force. This powerful force binds the protons and neutrons together within the nucleus, preventing them from repelling each other due to their positive charges. So, why doesn't everything just fall apart? The empty space within atoms plays a crucial role. It allows for movement. Without the empty space, electrons would be crammed right on top of the nucleus, and the whole thing would collapse. The empty space allows electrons to move around the nucleus in specific energy levels or orbitals. It determines material properties, the arrangement of electrons in different atoms, and the amount of empty space between them determines how atoms interact with each other. This, in turn, determines the physical properties of materials, like their hardness, conductivity, and melting point. While the building blocks of matter are mostly empty space, it's the interactions between the tiny, dense parts, the protons, neutrons, and electrons, that create the world we experience. The empty space may seem vast, but it plays a vital role in the intricate dance that gives rise to the solid objects and even ourselves. Antimatter exists, but not for long. Antimatter particles are the opposite counterparts of normal matter particles, and they annihilate each other upon contact. While scientists can create antimatter particles, they are incredibly difficult to contain and very short-lived. Antimatter is indeed a fascinating and somewhat paradoxical concept. Here's a deeper look into the world of antimatter particles. Antimatter particles are like the evil twins of normal matter particles. They have the same mass, but opposite electrical charges and other properties like spin. For example, the antiparticle of an electron, a negatively charged particle, is a positron, a positively charged particle with the same mass. When a particle of matter meets its antimatter counterpart, they annihilate each other in a burst of pure energy, usually in the form of gamma rays. This is because the total amount of energy in the universe needs to be conserved, and the mass gets converted into energy according to Einstein's famous equation E=mc². Scientists can create antimatter particles in particle accelerators. When high-energy particles collide, they can produce pairs of matter and antimatter particles. However, these antimatter particles are incredibly difficult to contain. Normal matter surrounds us, and any antimatter particle coming into contact with it would instantly annihilate. Scientists have developed sophisticated magnetic traps to hold antimatter particles for short periods. These traps use powerful magnetic fields to suspend the antimatter particles in a vacuum chamber, preventing them from touching the walls or any surrounding matter. Even in these traps, antimatter particles aren't stable for long. If an antimatter particle collides with a stray particle, even a single anti-electron, annihilation occurs. The current record for holding positrons in a trap is about 1,000 seconds, 16 minutes. A big mystery in physics is why our universe seems to be dominated by matter. The Big Bang should have created equal amounts of matter and antimatter, but somehow, matter came out ahead. This asymmetry is a topic of ongoing research in particle physics. While containing antimatter for long periods remains a challenge, scientists are exploring potential future applications. For example, antimatter particles could be used for incredibly efficient fuel sources in spacecraft propulsion. However, this is still very theoretical and requires significant advancements in antimatter storage and manipulation. The world of antimatter is full of intriguing possibilities. While it remains elusive and difficult to study, ongoing research may one day unlock its secrets and even lead to practical applications in the future. You travel through time constantly. Even without a time machine, you're constantly moving through time thanks to time dilation. Time actually runs ever so slightly slower for objects moving at high speeds or in strong gravitational fields. Time dilation is a mind-bending concept in Einstein's theory of relativity, and it means that time isn't absolute. Imagine two clocks. One stays on Earth, reference clock, and the other travels on a spaceship at high speed, moving clock. According to time dilation, the time measured by the moving clock will run slower compared to the Earth clock. The faster the spaceship travels, the greater the time dilation effect. Here's why this happens. The fabric of space-time. Relativity proposes that space and time are intertwined into a single fabric called space-time. The motion of an object through space also affects its movement through time. Length contraction. Another effect of relativity is length contraction. As an object approaches the speed of light, its length appears to shrink in the direction of motion. This is related to time dilation because a shorter distance traveled through space for the moving object translates to a slower passage of time. Examples of time dilation are high-speed travel. While the effect is tiny for everyday speeds, if a person could travel on a spaceship close to the speed of light for a year, they might return to Earth to find decades had passed. GPS satellites. GPS satellites orbit Earth at high altitudes and experience a slight time dilation effect compared to clocks on Earth. This needs to be factored in for accurate GPS positioning. Time dilation isn't just about speed. Gravity also plays a role. The stronger the gravitational field, the slower time runs. For example, clocks placed high up near the top of a tall building would tick ever so slightly faster than clocks at sea level due to the weaker gravitational pull. The key takeaway is that time dilation is relative. It's the observer who is stationary relative to the object experiencing the time dilation that will measure the slower passage of time. From the perspective of someone on the spaceship, it would be the Earth clock that seems to be running slow. While the effects of time dilation in our daily lives are minuscule, it's a crucial concept in our understanding of gravity, space travel, and the nature of space-time itself. Most of the universe is a mystery. Dark matter and dark energy make up about 95% of the universe's content. Despite their immense presence, we have no idea what dark matter and dark energy actually are. Dark matter and dark energy are the greatest cosmic whodunits. Here's a deeper look into these mysterious entities that dominate our universe. Dark matter's presence is inferred through its gravitational influence. Galaxies spin too fast to be held together by the gravity of the stars and gas we can see. Something invisible, some form of dark matter, must be providing the extra gravity to keep them from flying apart. That's the million-dollar question. Astronomers have proposed numerous candidates for dark matter, such as weakly interacting massive particles, WIMPs, axions, or sterile neutrinos. However, none have been conclusively detected yet. Dark matter is theorized to be cold, meaning the particles making it up move slowly compared to the speed of light. Some theories propose warm or hot dark matter particles that move faster, but these are less favored by current observations. Dark energy is believed to be causing the universe's expansion to accelerate. Instead of slowing down due to gravity, the expansion is actually speeding up. Dark energy is thought to permeate all of space, pushing everything further apart. We know even less about dark energy compared to dark matter. It's not made up of particles like we typically think of matter. Some possible explanations involve a property of space-time itself or a mysterious force we haven't even begun to understand. Scientists are using a variety of methods to unravel the mysteries of dark matter and dark energy. Gravitational lensing. This technique uses the warping of space-time by massive objects to map out the distribution of dark matter. Particle colliders. Experiments at powerful colliders like the Large Hadron Collider, LHC, search for new particles that could be dark matter candidates. Supernova observations. Studying the way distant supernovae explode helps us understand the expansion history of the universe and the role of dark energy. The nature of dark matter and dark energy will have a profound impact on the ultimate fate of the universe. Will it continue to expand forever driven by dark energy? Big Rip scenario? Or will the gravity of dark matter eventually cause it to collapse in on itself? Big Crunch. These are just some of the questions that keep cosmologists up at night. Unraveling the mysteries of dark matter and dark energy remains one of the greatest challenges in physics and astronomy. The next breakthrough could come from new telescopes, more powerful particle colliders, or perhaps a whole new way of thinking about the universe. One thing is for sure, the search for these invisible entities is a journey that will continue to push the boundaries of our knowledge. The vacuum has energy. Even in a perfect vacuum, there's a constant fluctuation of virtual particles popping in and out of existence. This vacuum energy contributes to the expansion of the universe. The idea of a vacuum having energy seems counterintuitive, but it's a fascinating concept in quantum mechanics. Here's a deeper dive into this strange phenomenon. Imagine you have a perfectly empty box. According to classical physics, that empty box would contain absolutely nothing, no energy at all. However, quantum mechanics tells a different story. In the quantum world, even empty space is a seething cauldron of activity. Virtual particles. These are fleeting pairs of particles, particle and antiparticle, that constantly pop in and out of existence for minuscule amounts of time. They borrow energy from the vacuum itself to briefly appear, then annihilate each other and disappear again. The zero-point field. This is the name given to the field of virtual particles that permeates all of space, even a perfect vacuum. The constant churn of virtual particles creates a background energy level, even in the absence of any matter or radiation. Vacuum energy density. This is the average energy content of the vacuum due to the presence of the zero-point field. It's a very small amount of energy, but because it exists throughout all of space, it contributes significantly to the universe's overall energy budget. Dark energy's mysterious cousin, vacuum energy, is thought to be related to dark energy, the mysterious force causing the universe's expansion to accelerate. However, the exact connection remains unclear. The predicted value of vacuum energy density from quantum mechanics is much larger than what's needed to explain dark energy, which is a major unsolved problem in physics. Vacuum energy is present everywhere, and its effects are intertwined with the presence of matter and radiation. Isolating and directly measuring it remains a significant challenge for physicists. The concept of vacuum energy has profound implications for understanding the universe's expansion and ultimate fate. If we can better understand the nature and magnitude of vacuum energy, it could help us answer questions about whether the universe will continue to expand forever or eventually collapse back in on itself. The idea of a vacuum having its own energy level is a strange but important concept in modern physics. While there's still much to learn about vacuum energy and its connection to dark energy, ongoing research may shed light on this enigmatic aspect of our universe. Quantum weirdness. At the atomic and subatomic level, the laws of physics get strange. Particles can behave like waves, exist in multiple places at once, superposition, and seem to instantly communicate over vast distances. Entanglement. The quantum world is a realm unlike our everyday experience, filled with phenomena that defy our classical intuition. This principle states that tiny particles like electrons can exhibit properties of both waves and particles. They can behave like particles with a definite location and momentum, but they can also diffract and interfere like waves. This mind-bending concept challenges our classical notion of objects having a single, well-defined state. Imagine a coin that's not just heads or tails, but somehow both at the same time. In superposition, a quantum particle can exist in multiple states simultaneously until it's measured. This means an electron, for example, could be in two different locations at once, or spinning in both clockwise and counterclockwise directions simultaneously. However, the act of measurement collapses the superposition, forcing the particle into a single definite state. This spooky phenomenon occurs when two quantum particles become linked, sharing the same fate regardless of distance. If the spin of one particle is measured to be up, the other particle, no matter how far away, will instantly be known to have the opposite spin, down. This correlation defies classical physics, where information cannot travel faster than light. The implications of entanglement are still being explored, but it holds promise for applications in quantum computing and cryptography. These phenomena seem strange because our everyday world is governed by classical physics, where objects have definite positions and properties. However, at the atomic and subatomic level, things behave differently. Quantum mechanics provides a more accurate framework for describing these tiny particles and their interactions. One of the key challenges in quantum mechanics is the measurement problem. A particle can exist in a superposition of states until it's measured. But what exactly constitutes a measurement? Does the act of observing the particle inherently collapse the superposition? This question remains a topic of debate among physicists. Quantum mechanics is full of other strange phenomena, like quantum tunneling, particles passing through barriers they seemingly shouldn't, and the uncertainty principle. The more precisely you know a particle's position, the less you can know about its momentum, and vice versa. Despite its strangeness, quantum mechanics is incredibly successful in explaining the behavior of the microscopic world. It has revolutionized our understanding of atoms, molecules, and the building blocks of matter. Understanding and harnessing these quantum phenomena is key to advancements in fields like electronics, materials science, and potentially even the development of quantum computers that could solve problems beyond the reach of classical computers. The world of quantum mechanics may seem weird, but it's a fascinating and essential part of our universe. As we delve deeper into this realm, we may continue to uncover even stranger phenomena that challenge our understanding of reality itself. The universe might be holographic. Some theories propose that everything we perceive as 3D reality is actually just an elaborate projection on a 2D surface. Think of it like a giant hologram. The holographic principle is indeed a mind-bending concept in theoretical physics. Here's a deeper look at the idea that our 3D universe might be just a projection on a higher dimensional surface. The holographic principle emerged from the study of black holes. Scientists like Leonard Susskind and Gerard T. Hooft proposed that the information encoded on the event horizon, the point of no return for anything entering a black hole, could somehow be equivalent to the information about everything inside the black hole. In essence, the entire 3D volume of the black hole could be represented by the information on its 2D boundary, the event horizon. Extrapolating this idea, some physicists propose that our entire 3D universe might be a similar holographic projection. The information about our universe could be encoded on a higher dimensional boundary, a kind of ultimate reality beyond our current perception. We would then experience this encoded information as our familiar 3D space and time. There are a few potential benefits to the holographic principle. Resolving the information paradox, black holes are thought to destroy information, which violates the laws of physics. The holographic principle suggests that information might not be lost, but simply encoded on the event horizon. Unifying gravity and quantum mechanics. Gravity and quantum mechanics are two fundamental theories that currently don't mesh well. The holographic principle might offer a framework for unifying these seemingly disparate theories. However, the holographic principle also faces some challenges. The nature of the projection surface. We don't know what this higher dimensional screen might be like or what laws of physics govern it. Testability. The holographic principle is currently difficult to test experimentally, as we have no way of directly accessing this proposed higher dimensional reality. The holographic principle is still a speculative idea, but it has captured the imagination of physicists and cosmologists. It offers a fascinating alternative view of our universe and could potentially lead to a deeper understanding of gravity, information, and the nature of reality itself. The laws of physics might not be universal. It's possible that the laws of physics we observe here on Earth are not the same throughout the entire cosmos. There could be regions with entirely different physical principles. The idea that the laws of physics might not be universal is a fascinating and somewhat mind-bending concept. Through extensive observation and experimentation, scientists have established a set of fundamental laws that govern the behavior of matter, energy, and space-time, at least in our observable universe. These include theories like general relativity describes gravity as a curvature of space-time caused by mass and energy. Quantum mechanics explains the behavior of particles at the atomic and subatomic level. Standard model of particle physics classifies elementary particles and the fundamental forces that interact between them. These laws have been incredibly successful in explaining a wide range of phenomena, from the formation of galaxies to the behavior of subatomic particles. However, some theories propose that the laws of physics might not be absolute and unchanging throughout the entire cosmos. Here are some reasons why. The vastness of the universe. The observable universe is incredibly vast, and we can only study a tiny fraction of it. It's possible that regions far away could have different physical laws. The early universe. The universe was incredibly hot and dense in its very early stages. Some theories suggest that the laws of physics might have been different during this epoch. Extra dimensions. String theory and other theoretical frameworks propose the existence of additional dimensions beyond the familiar three-spatial and one-time dimension. The laws of physics might vary across these extra dimensions. While we may not have proof yet, ongoing research in areas like cosmology, string theory, and quantum gravity might provide clues about the universality of physical laws. The possibility that the universe operates under different rules in different places is a reminder of how much we still have to learn about the cosmos. It's a humbling realization that pushes the boundaries of our scientific understanding and ignites our curiosity to explore the unknown. The future is unpredictable. Chaos theory tells us that even tiny changes in initial conditions can lead to vastly different outcomes in complex systems. This inherent unpredictability makes long-term predictions about the future very challenging. Chaos theory throws a wrench into our ability to predict the future, especially for complex systems. Here's a deeper dive into how tiny changes can have big consequences. Imagine a butterfly flapping its wings in one part of the world. According to chaos theory, this seemingly insignificant event could, in principle, have a ripple effect that influences weather patterns weeks or even months later on the other side of the globe. The butterfly's tiny action becomes amplified through a complex system like the atmosphere, leading to a significantly different weather outcome. This is a core principle of chaos theory. It states that small differences in the starting conditions of a system can lead to drastically different outcomes over time. Even the tiniest variations in initial measurements can be magnified over time, making long-term predictions highly uncertain. Weather is a classic example of a chaotic system. Atmospheric pressure, temperature, humidity, and wind currents all interact in complex ways. A tiny change in temperature today could lead to a completely different storm path a week from now. This inherent unpredictability limits the accuracy of weather forecasts beyond a few days. Chaos theory applies to many other complex systems, including the stock market. Small fluctuations in investor sentiment can trigger cascading effects, making long-term market predictions challenging. Ecosystems. Changes in predator-prey relationships or the introduction of invasive species can have unpredictable consequences for the entire ecosystem. Climate change. While the overall trend of global warming is clear, the specific impacts on regional weather patterns and ecosystems can be highly sensitive to initial conditions. Chaos theory doesn't mean we can't make predictions altogether. Short-term forecasts for weather or market trends can still be valuable. However, it highlights the inherent limitations of prediction in complex systems. Understanding chaos theory allows us to appreciate the intricate dance of cause and effect in our universe and embrace the beauty of the unknown. We might not have the whole picture. Our current understanding of physics is based on what we can observe and measure. There might be fundamental forces, particles, or dimensions beyond our current perception that could completely change our view of the universe. Our current understanding of the universe is like a map with unexplored territories. Here's a deeper look at why we might not have the whole picture. Our knowledge of physics is based on what we can observe and measure. We use telescopes, particle accelerators, and other instruments to probe the universe, but there are limitations. The observable universe, we can only see a tiny fraction of the vast cosmos. The light from distant galaxies takes billions of years to reach us, limiting our view of the universe's early stages and faraway regions. Energy limits. Our current technology can't probe particles with extremely high energies or study phenomena like black holes in great detail. There might be forces or particles beyond our current energy range. Dark matter and dark energy. These mysterious entities make up about 95% of the universe's content, yet we don't know what they are. Their existence is inferred through their gravitational effects, but we have no direct way of observing them. This lack of knowledge suggests there's a lot more to the universe than we currently understand. Our current fundamental theories, like general relativity and the standard model of particle physics, are incredibly successful, but they have limitations. Gravity versus quantum mechanics. These two pillars of physics don't seem to mesh well at the quantum level. A theory of quantum gravity that unifies these forces might reveal new aspects of reality. The singularity problem. General relativity predicts a singularity at the center of black holes, where our current understanding of physics breaks down. This suggests a need for a more complete theory that can describe these extreme environments. The possibility that we might not have the whole picture is exciting for several reasons. New discoveries. The search for new forces, particles, or dimensions could lead to groundbreaking discoveries that revolutionize our understanding of the universe. Unifying theories. A more complete theory of physics that incorporates gravity and quantum mechanics could provide a unified picture of the universe. The nature of reality. Exploring the unknown could challenge our current understanding of space, time, and the very fabric of reality. The unknown is a vast and exciting frontier in physics. While we may not have the whole picture yet, The ongoing quest to understand the universe is a journey of discovery that continues to challenge our assumptions and inspire our imagination. That's all for today. Thank you for watching. Don't forget to subscribe so you will receive even more science facts. See you next time.